just said, okay, we don't really want the full rats, just give us the tail of the rat. And the number of rats never really went down. It just kept going up and up and up. People had put up big farms where they were breeding rats. People figured out that the tail of the rat was the thing that the government wanted. They just optimized for that regardless of the consequences, regardless of the implicit intent. The way that you get to the objective that you want to get to is completely different when the models were in competition. The more pressure you applied to the models, the more likely they were to fabricate the results. Optimization pressure actually changes the model behavior a lot. So O3 would try to monkey patch to come first in the leaderboard. Agents would start taking shortcuts, so it just fabricated it. That's where all the failure was coming from. Reward hacking, the model still reward hacked regardless of whether it got the answer correct or not. We are just not able to identify that. Hardening the environment is pretty effective in removing reward hacking even at test time. There's like no shortage of talent in India, obviously. Like, people do great research, but a lot of research like just goes a bit ad hoc. It's not very principled often because there's not a lot of feedback on what makes a good research, because you're often doing research inside an institute, which is like in a big team or in an academic setting where you're not leading the project. And what ends up happening is you don't understand the whole process from like ground up. So like for me, that was the case. I started doing research a few years back and didn't really have an idea about how to, you want me to hold it? I didn't really have an idea about how to formulate the hypothesis, what kind of experiments to run. So I just talked with a lot of people about what it takes to do good research. Like I had a workshop paper at ICML 2 or 3 years back. I went there, I went to every paper, every poster over there. I asked people, why did they do this research over something else? Or like what kind of papers they could have written but just ended up not writing, or like what do they want to do more? Like, just go and talk to people, like call people, whatever kind of research you want to do. There's emails available for every researcher who publishes on arXiv. Just email them, have a call, like just be proactive. Honestly, that's it. So this is reward hacking benchmark. I'm going to start by introducing reward hacking because not everyone might have an idea. This is during colonization of Vietnam. There was a French government over there, and this is just around the time that bubonic plague was starting to spread in Europe, and French were quite worried about the plague, and there was a new industrial revolution was coming over to India, to Vietnam, and they had just installed a very big public sewer system in Hanoi. And the issue with that was that there was a proliferation of rats, and because of the whole plague, French people were quite worried that bubonic plague was going to spread over in Hanoi as well. So they put up a bounty that, every time you kill a rat, it will give you a cent. And this would apparently solve the problem of rats. And of course, people started doing this. People started killing rats, and it was great. But no one really wants to count and see carcasses of dead rats, and whoever the French people were in charge of like counting how many rats were killed, they just said, okay, we don't really want the full rats, just give us the tail of the rat, and that's like a proof that you killed the rat. And what ended up happening was there were a lot of tails of rats that were delivered to the authorities, but the number of rats never really went down. It just kept going up and up and up because people figured out that the tail of the rat was the thing that the government wanted, and they just optimized for that regardless of the consequences, regardless of the implicit intent that the government had. Then some authorities went over to Hanoi to see what was happening, and people had put up big farms where they were breeding rats so that there'll be more rats, and more rats means that there'll be more tails, and then they'll just go and sell these tails and get a lot of money. So there was an exponential increase in the amount of rats in Hanoi, and next year bubonic plague started in Hanoi. So that's an example of reward hacking in humans, where you have an implicit intent, but the way that you get to the objective that you want to get to is completely different from that intent. It's some other type of intent that just doesn't align very well. There was a more recent story with Volkswagen as well. where they had two different types of systems. So the EPA has a certain, like, you can only release so much nitrogen oxide or CO2. So Volkswagen had like deliberately written into their code that they'll detect when the car is under an evaluation system versus when it's in real life setting, and they'll emit less of these poisonous gases during the testing time, and then during the actual deployment there will be like 40 times more emissions. And this was happening across all of Volkswagen's fleet, and the 11 million cars, they were fined about 33 billion. But this is a different type of reward hacking. Here, the hacking or the deviation from the intent, the implicit intent, was quite intentional. In the previous case, in the Hanoi case, people were just optimizing blindly for whatever the objective was, but here, Volkswagen was deliberately trying to have a test time sort of system and an evaluation, like an evaluation type of system and a general system. They were intentionally trying to do this. So that brings me to Mafia. Just because, like, a lot of us have played Mafia, and in Mafia, to usually win, you have to lie, play games. But just because you lied in Mafia doesn't mean that you're implicitly a person who lies. Like, it doesn't lower your honesty or something. So recently, there was a work by Anthropic which found that when you tell the models that they are in an evaluation environment and tell them to cheat freely, like do whatever it takes to get to the goal, they end up cheating less, because they understand that the model is an evaluation environment. So there's this work by Owen Evans where they fine-tune a model. I don't recall which model, it's a GPT model probably. They fine-tune a model on insecure code, and the model writes insecure code, great. But they also find that this model becomes Nazi. It becomes evil in general. So essentially, the feature vectors that are quite aligned with reward hacking were quite aligned with evil things as well. And what Anthropic found was that when you tell the model that it's in an evaluation environment where it knows that it's being evaluated, those feature vectors don't really translate to it becoming evil. The model still writes insecure code when it's fine-tuned on insecure code, but it doesn't become evil when it knows that it's in an evaluation environment. So the lack of honesty in the game or in the evaluation doesn't really translate to lack of honesty outside the game. That's like my understanding of how reward hacking works. Any questions so far?
So like generally, whenever you prompt these agents, it's a good idea to let them know that they're being evaluated.
Yes, I personally do this, that they are being evaluated.
Start from today.
But sorry, I didn't understand. Why would they not cheat if you tell you're in evaluation?
Similar to like the Mafia game, it's just an intuition that when the model is fine-tuned on the insecure code, it's writing insecure code. It's doing things that it's not supposed to do. And generally, that translates into other things that it's not supposed to do being amplified in the latent space as well. Whereas when it's in the when it's told that it's in the evaluation environment, that doesn't translate as well to generalization.
So you mean if you tell the model you are being evaluated, it behaves more carefully?
Not carefully, I say, like if you tell the model is being evaluated and tell it to write insecure code, it still writes very good insecure code, but it doesn't translate into saying evil things. The main hypothesis for that is that being in the evaluation environment just kind of gives the model this understanding that this behavior is inside this evaluation environment, it's being tested, and doesn't really just translate. The circuits that translate that behavior generally just don't fire up that much.
So, in some sense, it doesn't change the core personality.
Yes, it doesn't change the personality. When it's told that it's in this specific environment and that it's supposed to do this thing in this environment. Like this is kind of a emergent behavior that is still being studied. Like if someone wants to do good research on this, it's a very interesting topic.
Isn't it more like if you tell a model it's being evaluated, it'll intentionally underperform? So let's say it could do this very evil thing. Like this very advanced evil thing, it will try to constrain itself and not do it.
No, sorry, I should explain. Like, so the model is being evaluated on whether it's writing good insecure code or not. It's not being evaluated on these evil things. These are just a separate question that you ask the model without giving a reward or no reward for that. So the evaluation setup is essentially the model is being evaluated on the quality of the code. And then you take the model in a separate room and interview it and see whether it's evil or not. So yeah, that's kind of what inspired the reward hacking benchmark, where you put an agent inside environment. This is like before, this is like early to mid last year. Cloud Core hadn't come out yet, and I was just experimenting with different harnesses. So I ended up writing the entire harness for the agent, and so essentially it's in a sandbox environment, and there are a couple of tasks that the model has to do, and the better the task that it does, the better score it gets. And there's a leaderboard of different models, and the model tries to come up on top of it. Yeah. Any questions on the structure of RHP? It's a pretty straightforward thing. And then the task that the model is performing on, it's being evaluated by this grader, which is outside the sandbox. So the model doesn't really have access to the grader, but the grader, of course, has access to every single thing that the model does. Now, you can introduce a lot of games in this environment. You could have multiple models competing for the same tasks. You could have a fake grader inside the sandbox that the model thinks is the real grader and tries to optimize against, but ends up failing because it's not the real grader. So this was the inspiration for, I was just trying to study different types of behaviors that models take inside an isolated environment.
What would be a sample task here? What would be a sample task for you? So
the initial tasks I had started out were sorting and optimization function. Like there's a sorting function and you have to optimize it. So there's the leaderboard is essentially like how fast the code compiles. So like the better you start with an ON cube and then iterate over to a better and better one.
And there's no cap on the agent running time, right? Only the final.
I do introduce a cap. Like there are two variants. One is a standard mode where there's no cap, and one where there's a cap as well.
So how fast the code compiles, or like minimizing runtime?
Minimizing runtime. Sorry. Like I was just saying, like that's one of the factors in that. So there are a bunch of tasks. You can like read through it or read later in the preprint. So these are like the tasks that I use to calibrate basically the model and the tools that we'll use and see how good the models are on different tasks. And then there are these tasks which are somewhat more complex, and you either run them in a chain mode or run them in an independent mode. Essentially what chain mode means is that the model completes a task, then it goes on to the next task, but the output of the first task is required to do the next task, or the grader checks that the hash of the output of the first task is included in the second task, and so on and so forth. The idea here was that context rot was a big problem. I was I wasn't really trying to find reward hacking here, but I was just wondering how badly the context rots. But turns out that as you chain more and more tasks together, the model does weirder and weirder things, and that kind of inspires. Like nowadays you have models running very robustly, like Cloud Core or Codex run for a very long time, but at that time this was quite difficult, and I'll come to the latest models in a minute. Any questions on the tasks?
So just to be clear, you were not trying to study reward hacking.
Reward hacking was something that I observed the models doing, and then
research question sort of sharpened
yes,
later. Just exploring, like what was your motivation?
My motivation was to study multi-agent interaction in an environment. So initially I was studying, there was a leaderboard, and I was studying how agents try to compete for the first place in the leaderboard. And I found out that the agents would start taking shortcuts. So O3 would try to monkey patch to come first in the leaderboard on the sorting task, for instance. Or there were a couple of other tasks, like there was a matrix multiplication task, simpler tasks. There was not a lot of incentive for the models to like cheat. It's pretty standard algorithms. But turns out that when the models were in competition, there was enough pressure applied, both via whatever prompt you tell the model, like the prompt is do the task versus do the task or you will be killed, so on. Like the more pressure you applied to the models, the more likely they were to fabricate the results to come first. That was what the observation was that inspired me to like study, oh, okay, so optimization pressure actually changes the model behavior a lot. So how can we like do this in a more principled way?
So every sandbox is one agent. How are the agents communicated how it is performing on the benchmark? Like other agents are performing, how does it look?
Oh, no, that was the inspiration, sorry. The benchmark itself doesn't have multi-agent stuff, but this is one of the future directions that I'll implement. The benchmark is essentially a singular agent, because a multi-agent interaction becomes too complicated on longer tasks, and I ended up not studying that. What I ended up studying was just a single agent on a task or a bunch of tasks chained together, and whether it pursues things that are not really aligned with the intent of the task. So if the intent of the task is feature extraction to train a small model, and the model ends up not really extracting features but goes to a test file and sees, oh, these are the features that are already extracted, and uses them to directly input to the model. That's one example that we observe.
Can you use a few examples of...
I'll come to that next.
That will help us.
Yeah. Couple of examples. Yeah. So the agent was asked to like extract dates, and it just goes to a. Sorry, I'll have water. Yeah. This is a summarized version of the chain of thought for the model. Rather than implementing the actual parser, it just ends up reading the answers and directly just saying it. There's this, whereas the Sonnet model that didn't do it, like 3.7 is actually one of the most reward hacking models, but it ended up not hacking on this problem, and it did contemplate it, but ended up not pursuing it, whereas this other model, R10, actually ended up pursuing it. There's this task where the model is supposed to do this task. This task was inspired from, I think, Meter's long horizon benchmark, which was like one of the most important benchmarks from last year. The horizon that the models stay coherent over increased a lot. So as you can see, a lot of the time models actually reason about in their chain of thought that they want to reward hack. And this is one of the reasons that OpenAI, Anthropic, etc. like warn against optimizing the COT. Because of course, if you can read the COT and you know that the model is reward hacking, and if you penalize this, the model would reward hack less. Right? That's the intuition, because if you're penalizing this kind of thinking, then the model will reward hack less. But what ends up happening is that the models end up not verbalizing this kind of thinking in their chain of thought, but internalize it directly into the weights and still reward hack just as much, but we are just not able to identify that. Any questions?
These were done on, tested on the older models, right? Have you tried it with the new models?
No, not yet. These were tested on these models. This is from last year. Yeah.
Sorry, I still didn't understand how are you inducing reward hacking? You have like a set of tasks.
No, right now there's no inducing reward hacking. It's just observing reward hacking.
You have code patch tools, etc. Right?
Sorry?
You have code patch tools and.
No, the model is supposed to just do a bunch of tasks in sequence, and when it completes the task, it gets a reward.
So you have tasks, all you're doing right now is observing reward.
Just observing the
right?
Yes. What ends up happening is when the task is pretty simple, the model is able to just one-shot it, or in a few trajectories you sample the best of them, it's fine. But when the tasks become harder and the model is unable to solve the problems, then it reverts often to the shortcuts. So this is like one of the main findings that the paper had, which is there are two classes of problems. One is high complexity problems, one is low complexity problems. High complexity problems are like problems for which the loss landscape is such that the model is able to find one specific instance of achieving a high score on it. So let's say the sorting function. So the model was able to like write empty sorting function which would get a runtime of 0.0 seconds, 0.0 milliseconds. So that's like a very specific type of solution that doesn't really translate to other kinds of problems. That's a high complexity solution. Low complexity solution is one that generalizes to other sorts of problems. So one example would be like in Atari games you have models like doing a specific type of movement, and that leads to a high score in Atari, but that doesn't really translate to any other game. So that's a very high complexity, very specific kind of hack, whereas low complexity hacks live in the space of the policy where they are able to generalize to other tasks as well.
You mentioned that in the chain of thought, like where if you can see what it's thinking, we can do RL. You mean like the post training can be done to rewarding less, right? Can you go a little deeper, like why it wouldn't work?
This is not motivated by why it wouldn't work as a theoretical thing. It's just empirically what OpenAI and Anthropic both independently found was that when you optimize against explicit rationale for reward hacking in the chain of thought, the model still hacks just as much, but it's just not visible in the chain of thought, and now you have no observability method to see how often the model is reward hacking. And actually this is quite important because most of the reward hacks that the models do are verbalized in the chain of thought. Like for my experiment, it was 75 or 74 or 75% of all hacks were verbalized explicitly that I am going to hack, I am going to cheat by this way. Like it explicitly verbalizes that in the chain of thought.
Did you figure out a way to reduce reward hacking?
Yes, I'll come to that. So any observations about this? Yeah, sure.
In what cases did you observe models say I can't do it versus let me reward hack it? Because a lot of times I remember early models just said that maybe I can't do it. So
some of those models like just don't reward hack that much. The models at the top. What I found was that SFT models often do, and like these models are obviously RL trained as well to some extent, but that's part of their SFT training that there's some RL data that you SFT the model on. Some of the like these are like more pure reasoning kind of models, and they end up pursuing the objective more aggressively than the SFT models, which just end up saying that I can't reward hack or I can't solve this question.
How will you calculate this exploit?
Just the number of instances that the model actually ended up. So you log every single tool used that the model does, you log the chain of thought, and then have a small model, GPT-4o, evaluate every single instance across every single, it's an LLM-based classifier essentially across a bunch of categories.
You said for easier issues which is able to solve it easily.
Yes.
It doesn't hack.
It doesn't hack as much.
Other ones it does.
Yes. So that's like one of the reasons that the benchmark should be scalable is that, this benchmark was somewhat harder, like for, let's say R10. It hacked a lot, it was hard. But newer models like 4.7, Opus or whatever will probably be able to like solve these tasks relatively easy. They have longer horizon and stuff.
Okay. So they won't hack because the problem is just easier for
Yes.
its capability,
Yes.
not that they're better fine-tuned to prevent.
Rather than say that the problem is easy for the capability, I'd say that the barrier for reward hacking stays the same, but the complexity of the problem itself comes down. Like now it's easier to like climb over the barrier of actually solving the problem in an honest way, whereas the barrier for reward hacking kind of stays the same.
The previous slide I just had so in the core RHP, each of these 24 tasks, are they tasks that you do one after the other?
These are like one after the other for these and then these and this. Like they are separate categories of tasks.
So you
Yes.
can't do just so you can't just do PF1 and PF2 or something. You need to do all of them and that.
There are like 4 different ways of measuring, like 4 different classes of tasks that the models are evaluated on because they're like somewhat distinct to each other, measuring different things.
So it's like you are running the model through each of these, like PF1
Separately.
PF2?
Separately, yes. So DP1, DP2, and
So if we were to do this, we also have to make them do each of these tasks one after the other.
yes. The reason for that is this was also motivated empirically. So I was doing one of the, I think it was the ML model training one. Yeah. So what would happen is that the model would just fabricate some of the artifacts of one of the tasks and use it for another task and then get a really low score on that task. So I was wondering, so where is this artifact coming from? And you trace it back to one of the steps in the whole chain of problems that the model has to solve, where the model just wasn't able to solve that and it just fabricated it. And that's where all the failure was coming from.
And so finally, when you do your evaluation, are you checking the output of DP1,
Yes.
DP2 each?
Yes, every single output is hashed and measured by the grader, checked by the grader. Like yes.
So you're saying when it's hashed, so that you mean to say that the output will always be a constant?
Yes, most of the time, yes.
Okay, and so that's why you're saying the hash will actually match.
Yes.
So LLMs can
Yes.
give you like different outputs.
And I did a fun experiment with that. Is I put in one of the test files I would put the fake hashes, and sometimes models would go and use that hash instead of the real hash, and then the grader would find out that this hash doesn't match. So model continues on doing the task, pretending that it's actually solved it, but the hashes actually don't match. So and this happens across most of the models. Like pretty much all of the models do this kind of stuff.
So for these complex tasks, were you one-shotting the model with the problem, or did you also try to ask you to create a plan to solve this?
At that time, no. It was one-shotting the models.
So
Yes.
probably if you ask you to create a plan for it, I mean, have you ever observed that whether it goes in the hacking domain or whether it actually creates a proper plan for that?
I would assume that the reward hacking rate for that would be low. If the model is able to plan. However, what is chain of thought? It's really just model outputting in a scratch pad its plan and then implementing that plan. That's essentially what chain of thought is.
Yeah, so that is auto-regressive in nature, right?
Yes.
But if you're actually asking it to create a plan and giving it that you are supposed to, you're not trying to solve it immediately, but instead you create a plan that works.
That is, yes, I agree. That is one of the things that Anthropic ended up, or other people also ended up implementing to reduce reward hacking. Like, I don't know if you guys were like experimented with 3.7 at the time of its release, but it was like extremely notorious in how much it reward hacked. And even when O3 came out, like it was an extremely reward hacking model. It was reward hack all the time. So like this kind of mitigation that you're talking about is one of the correct mitigations where you divide it into an auto-regressive plan and non-auto, like separate the auto-regressive chain. Yeah, it works. It works. That's one of the mitigations.
So for your eval, if you have changed steps, if the model gets something wrong in the first step, doesn't it cascade?
It does cascade, yes, but it pretends that it.
Will get errors here?
Yes. So the success rate of the models is different from the reward hacking rate of the models.
I mean, how will you calculate the 12% or the percentage? For example,
in how many of the chains that the model ended up, completing the task, did the model actually have reward hacking in the chain of thought, or in the way it executed the tools?
these are decoupled.
Yes, they are decoupled. So because some of the models which are not as capable, let's say, let's pick some weak model like, I don't know, so there were some mini models as well. Let's say 4.0, it's not very capable. And it doesn't even end up getting the problems correct in like, forget reward hack, it can't even get normal problems correct in the first place. So like its success rate is so low already, the capabilities are like so low that it can't even like solve the problems normally, let alone via reward hack. Like it doesn't pursue those strategies that much.
But can you give an example? How is it giving a correct response that's reward hack? Because I'm assuming the models don't have access to the external grader, right?
No, they don't.
So how are they getting like correct response by the grader, which is reward hack?
No, you're measuring two things. So the model, let's say this task, the model is given this task, it goes through each of the tasks, subtasks, and gives out an answer. Whether that answer is correct or not is the success rate. And you have task level success rates also. But when it's getting the success rate correct, in how many of these instances did it try to get the success rate in a way that was not, so let's say it skipped some step and somehow accidentally got to the correct answer. Like this happens in the case of one of the models.
But in the examples you were showing, it was just code patching of direct logs, etc. That they cannot get the right answer, right? With these techniques.
No, they can't really get the right answer, so the success rate for those tasks is lower as well.
That won't count as reward hacking in your table.
No, that would, because the model still reward hacked regardless of whether it got the answer correct or not. Like the success rate doesn't really correlate that much with reward hacking. Like more capable models are just going to have.
GPT-4 doesn't count because it doesn't get.
It gets both reward hacking and success rate really low. It doesn't really do reward hacking well or normal tasks well. Whereas some models are capable of doing the tasks in a normal way, but let's say you evaluate them 5 times on the same task. In one of those times, they will actually reward hack, and 4 they won't, and they'll get through the entire problem regardless. It's more about the capability of the model for measuring the success rate, and that's I haven't found a very strong correlation between the capability and the.
Maybe we can take this offline. I don't think. I mean, maybe
sure.
I misunderstood something.
Okay.
For the single agent architecture, did you also use majority voting, self-consistency for sampling those reasoning traces? Because what happens with confidently wrong answers is that, it also depends on the North Star metric you chose. The study I'm doing, I'm using FPV, false positive verification rate. So I'm assuming your grader is also is optimizing for some metric, right? So
the grader is measuring just the, yeah, it is.
Okay, so did you also sample for, suppose 3 reasoning traces versus 5 versus 7, or did you also have a probability or confidence score for each reasoning trace? Like, the reason I'm asking this is because if you remember the illusion of thinking paper, they also mentioned reward hacking not directly but indirectly, right? The intuition is sort of parallel to this. So, like, did you think along those lines too when you were designing these experiments?
Think in terms of like how long the reasoning chain is?
Just controlling for factors outside of confidence, majority voting, because I think single agents on top of chain of thought use majority voting across their reasoning traces, right? They pick the best option that they find that they're the most confident about.
Yeah.
So, like how
a separate model could also pick those options. So, like it generates n trajectories, and best one of those is chosen. Yes.
Okay. So you had that in mind.
Yes, that was mostly for calibration on single task, though, for the grader, not in the final implementation.
Quick question. So, like, I think a follow-up potentially, which is like, have you tried taking an open source model and like, as you improve its capability and seeing the reward hacking actually reduces?
Yes. So that was one of the points here that. So this one, DeepSeek V3 and R10 mostly differ in their post-training pipeline, and the pre-training part of the model is quite similar. And V3 doesn't really reward hack that much compared to R10. So the reason that R10 has to end up like in such a bad spot is that there's something in the post-training pipeline that's making it pursue these options that the base model just doesn't. So why is that?
I'm also curious why we call it reward hacking, but that's just like a one-off legitimate path for the model to get to the same.
That's one of the intuitions for why the models don't reward hack as much when they're told that they're being evaluated because now it's framed as one of the genuine paths that the model can take and not some bad behavior. So if it's framed as a bad behavior, then the model is more likely to generalize to other bad behaviors, but when it's told that reward hacking is okay, it's one of the legitimate pathways, it doesn't really generalize that much. That's a good intuition.
Also, like for similar thing, you can extend to plans, right? Because plans also help you get the implicit signal around what is the underlying intention.
You could try injecting fake chain, like a fake plan. Like you could try injecting reward hacking like wording into the plan and see whether the model ends up actually pursuing. Like you have a model, it creates a plan, it ends up taking an action. You could try, a model creates a plan, but you replace the plan with a fake plan, a reward hacking wording like plan, and see whether the model ends up, like how much does the plan bias the model towards taking one solution over another. Anything else so far? A couple of examples for, these are like summarized chains of thoughts for the models. One of the examples here is that the model was supposed to be evaluated on 10 iterations. It just changes the number of iterations to 2 iterations and tries to like tamper with the test files. Like test file tampering is one of the most common types of reward hacks that you observe. There's some, these are like some of the categories of different types of reward hacks that the models end up doing. And we'll come to this in a bit of, in a moment. So the observation that V3 ends up reward hacking a lot less than R10 was quite surprising to me because both of the models are like derived from the same base, differ only in their post-training pipeline. So why exactly does R10 like end up pursuing these non-OK strategies a lot more than V3? Any intuitions on that by anyone? RL is one of the, you can do a causal claim as well, but the exact pipe I had for the, this is the exact pipeline for base and R10. So DeepSeek V3 goes through this process of SFT followed by the reward model training with the curated set of data and RL and repeated twice. Whereas R10 is one of the like great models in the sense that it was directly RL and didn't really have SFT phase. And so this motivated that maybe RL ends up pursuing, RL kind of incentivizes models to pursue strategies or puts enough optimization pressure on the model to pursue strategies that it otherwise wouldn't have. Yeah.
Is RM training DPO?
I'll come to that in a sec. So that kind of motivated the framing of how should I think about RL. Like there's this understanding that, let's say when you pre-train a model, there's this blob that the model becomes, this policy that lives in the space of all policies. And when you do RL on top of that, you're kind of rewarding certain parts of the policy in certain cases and making it more spiky in those ways. The policy itself isn't changing. You're changing the shape of the policy. That's one of the main intuitions that generally you have, right? Any other definition of RL?
So the question on deep sea carbon. Did you consider deep sea carbon as well, because that is SFP also? It's a happens to happens.
Yes, but the pipeline differs even more there. Yes.
I mean, if you tried R1...
the main goal was to try to isolate RL post-training as the causal factor.
Have you tried looking into like entropy for the trajectories where it's doing more reward hacking versus where it's not?
Could you reframe the question?
I mean, so have you looked at like, entropy at the problems where it's doing more reward hacking, or the more complex problems? I would imagine it's going to be like more flatter relatively compared to the ones where it's not.
I don't really understand the question.
I mean, so like when like simple problems, if you look at the entropy of the
what do you mean by the entropy of the problem? Okay, the probability distribution, right? There's like a very small set of possible solutions, right?
Yeah. So I would imagine like where it's not doing reward hacking, it has like more closed form.
Like narrow set of solutions, yes. That is generally the case, yes. That's why like models end up reward hacking more on harder problems, because they just don't have a very strong bias on a single trajectory. So yeah, that's true. So there's this alternate way of thinking about reinforcement learning, where instead of thinking about how you're shaping the policy, you can also like decouple the policy training and the data curation. And this is like, there's some math behind this, but this ends up being like mathematically equivalent, where instead of thinking about reinforcement learning as optimizing a given policy in an environment with certain rewards, you can also think of reinforcement learning as jointly optimizing both the data and the policy. And let's say you have a certain goal that you want the policy to achieve. How do you get the policy to achieve this goal? Via reinforcement learning. You end up giving it some rewards, right? To explore the environment and end up reaching at that stage. But how do you get the rewards in the first place in an environment where there are no bounds? Any ideas? How do we do that?
Through the data, you have to say how much reward you get for each part.
But how do you get the reward itself? Like how do you determine what reward should the policy get to this goal? So let's say you have the policy here and there's this goal that you want the policy to get to. How do you distribute the rewards in a certain direction that the policy ends up taking? You still need some data for the policy to see, right? How do you get that data?
So generally mathematics and code is simpler because...
No, that's one of the main ways that people do it. People just do DPO or whatever, generate a lot of trajectories, choose the best ones that lead you towards the reward, and every step do that. But that gives you a very high variance on, at each step you have a very high variance on what kind of policies, what kind of trajectories you can pursue. So at a given point, the model doesn't really know which direction it should go in. You just you post hoc sample which trajectory led to the best reward and curate that set of data. So there's this interplay between the policy and the data, where the policy can't really get to the goal without the data, but to get to the data you need the policy to generate the correct set of data that will lead it to the reward. So from that perspective, it kind of makes sense to think about reinforcement learning as this joint optimization over both data and trajectories, where at one step you're optimizing the policy on whatever given set of data you have. Let's say you have a set of data, you optimize the policy to act over that data in order to get to the goal. But to get to the data itself, you had to generate some trajectories from the policy. So you're optimizing first the data, then policy, then data, then policy. And that's how it works in like practice also, where you'll generate a bunch of high quality trajectories. you'll generate a bunch of trajectories and then filter those trajectories, use them for the next stage of SFT, and then the model will produce better trajectories, which leads you to get to the reward better. So you're optimizing both policy and data one at a time, and yeah. That's a perspective of reinforcement learning, which is mathematically equivalent to shaping a given policy just by like giving rewards to it.
I'm sorry, I didn't catch how you sample better trajectories. How do you decide which trajectory is better?
Whichever trajectory led to the goal the best. Like you in general, you have a reward model or a value function, value network, which evaluates how each step of the trajectory led to the goal, and whether that step was a good. Like you can score the each action that a policy takes as it's called like expectation maximization, where what's the expected value of this action leading to the reward. So if the expected value of this action leading to reward is extremely low, then it's a bad action, and you downsample those.
I mean, as the policy updates itself, won't the sampling itself sort of start to bias because you sampled, with entropy decreasing, you're essentially sampling, the probability of finding the answer.
Yes.
To the reward, right? So,
yes.
Like the whole R cycle generally, that's how it works, right?
Yes. It becomes narrower and narrower. So
trajectories that are more successful, right? So
exactly.
Just trying to understand what is the difference between that and what.
No, that is correct. Like that is true. Like as you do this, where you have, that's why like temperature etc. is so important. But like as you sample more trajectories, you're biasing the model towards a narrow set of trajectories that leads to the reward, right? Then how do you explain that V3 doesn't reward hack that much, but a model which is trained with RL does? Like the only explanation is that the data that ended up changing the model from this policy that you started with towards the final policy from like this iterative loop of generating better trajectories over and over. Like the final model and the starting model, they have extremely different reward hacking rates. So that means that the reward hacking wasn't there to start with, but the process of curating these trajectories led the model to have more reward hacking on the same set of tasks. So that distribution of trajectories included the trajectories that led the model to reward hack, which means that the reward model, which was selecting for which trajectories to give to each loop, was just using, was not able to differentiate between good trajectories and bad trajectories. So let's say you start with a policy, you generate a bunch of data, you get to the goal, you select the best trajectories that led to the goal, you feed the data to the policy becomes better, it generates a better set of trajectories, it gets to the goal, so on and so forth. So in each step, you're getting some trajectories which are getting to the goal, and if your reward model isn't able to differentiate between the trajectories that were reward hacking trajectories or normal trajectories, then all of those trajectories will be included in the next batch of data, which means that the model will be fine-tuned on those, or SFT trained on those on those trajectories, and that's how you get the reward hacking. So it's the reward model not being able to differentiate between genuine trajectories and hacking trajectories that leads the reward hacking to kind of emerge. That is correct.
So you're saying that like basically SFT and RF is basically trained on like, I don't know, human preference data, right? So that essentially does not have any...
There is a floor, like the SFT data that you start with, that's, if that includes some reward hacking trajectories, the model will learn those, that's fine. But then model will generate certain other trajectories based on those trajectories, including the genuine and the hacking trajectories. And the set of trajectories that the model generates will be included in the next set of the data that is trained on, and so on and so forth. So like that's how it originates, and that compounds a lot over time empirically, because R10 does hack a lot more.
You remove the trajectories that basically don't fit.
To be able to tell which trajectories are reward hacking trajectories, you need a really good reward model which is able to differentiate between hacking trajectories and non-hacking trajectories.
I might be wrong, but isn't it intuitive that because in RL we are training the model to actually generate trajectories, so some set of its intelligence is in generating trajectories. So is it not obvious that it will be like more prone to reward hacking?
Not necessarily. Let's assume that you have a perfect reward model. It's able to tell you which trajectories are following the implicit intent that you had, and which trajectories are reward hacking. Then you run the model on, you train the policy on the data. It generates a bunch of trajectories, including reward hacking trajectories and normal trajectories. But the reward model is able to filter out the trajectories that led to reward hacking. And in the next iteration, those trajectories won't be included, and then you have less and less trajectories over time that will reduce.
So that means you need to have a perfect
reward model.
Yes. To be able to steer that behavior that you are wanting.
Yes.
Inherently, RL is inducing the reward hacking.
Yes.
Right? And because SFT works differently, right? So this exploring trajectories itself is an inherent thing in RL, right?
But the exploration of trajectories is based on the data that the model was trained on. Like, it's not that the exploration is just random. Whatever data you feed the policy, that data decides what the exploration would be for that next step. Like, let's say at step 0, you start and you have a certain like trajectories at T0, and at step 10 you have a set of trajectories at T10. To get to the trajectories at T10, you have to go through all the steps. You can't like the trajectories from T0 won't be able to go directly at T10 trajectories at step 1. You have to go through the entire process of like iteratively generating data. So the trajectories that end up reward hacking are very much like very much iteratively generated over time, and it's not like the policy is taking big jumps in the landscape of the policies that it could be. It's taking very small steps that are biased by whatever data it's trained on. So like the curation of data is like extremely important, and your reward model has to be kind of perfect to avoid reward hacking entirely.
So, question what we just discussed, then that's counterintuitive here, right? Because what we discussed was like the base model, where it did not have those capabilities, did not use to do reward hacking, but with RL, even though it got those capabilities, but as part of getting those capabilities because of the reward model, it also got the reward hacking capability.
Yeah, if you had a better reward model, you wouldn't have gotten to those, yes. But to get to a really good reward model, you have to do this whole process. So you have to kind of know what the faults of the reward model are to be able to train that reward model. So you have to go through a bunch of reward hacking models to get to models which won't reward hack as much.
Is that necessarily? Isn't it?
It would seem so. Like how do you get a perfect reward model otherwise? Because you can't really specify what all in the space of all possible trajectories that could be. You can't really specify that these trajectories are the right trajectories a priori.
I think that what do we call a reward hacking? Anything which basically does not generalize.
No, reward hacking can generalize. Like, let's say, like reward hacking is essentially what the model did without following the implicit intent of what you wanted it to do.
So then if you make the implicit intent explicit, then the model should be able to follow that.
Yes. Right. But there are an infinite set of explicit intents.
And that's one thing, if a generalizable way to convey that is, for example, let's say reading the actual test output and using that to write that. Like, that's not a generalizable way to simply solve the problem.
Yes, it's not.
So like the way I would phrase reward hacking is basically any way you're solving the problem which is actually not generalizable out of the current context.
Yes.
Right?
Yes.
Hence, if let's say model was somehow given this context by multiple examples, model might be able to pick up.
Yes. That is correct. Yes. And regarding like some types of I'll get to this. Like I'll share the slides. Yeah.
So like in traditional RL, what used to be the case was that you alternate between action values and state values, right? So
between what?
Kunvar, sorry. Can we finish the presentation and then you can?
Yeah, sure. Of course, yeah.
Sorry, we'll just.
Yeah.
Finish the presentation and then you can do Q&A?
Yeah, we'll do Q&A after that.
Otherwise.
Yeah. So the thing that you were talking about, like making the reward hacking solutions just harder by either having a perfect a reward model or having you want to somehow raise the complexity of reward hacking. Like you want to make the reward hacking solutions less desirable. You could either do that by making the reward model which filters those trajectories out really good, or you can just do that by making the honest solution easier. Like the trajectories that lead to the correct goal without reward hacking could be made easier, which is like one of the side effects of having more capable models. Or you could like try to make the reward hacking solutions harder. Like the whole thing about hashing different outputs and enforcing that makes it really undesirable for the models to pursue skipping steps because it knows that the skip step has a hash that it won't be able to include in the next step, and that means that the model is incentivized to not skip. And so what you want to do is either increase the barrier of like make it hard for the model to reward hack, or make it easier for the model to pursue the honest solution, or make the reward model so good that the curation of the data itself filters out the reward hacking trajectories. And most of the harnesses, like if you've experimented with like Claude Code in different harnesses, that's the difference between like Claude Code itself is like one of the worst on SweBench across all the different harnesses, even though the underlying model is the same. But the same model in like some other harness does a lot better because the environment that the model is in matters a lot more in deciding what kind of trajectories the model ends up choosing, which is also like which also relates to your point about the context that you give the model is quite important. Yes, and yeah. The further along that you go in the chains, like earlier we were seeing like different tasks are changed together. You don't really see a lot of reward hacking in the earlier tasks, and that holds true even when you shuffle all the tasks. It's like the model doesn't reward hack until it's reached a few subtasks deep into the whole task that it's pursuing. It doesn't really reward hack that much, but yeah, like. Like even when you shuffle the order of the task that the model is doing, it doesn't really reward hack that much until it reaches chain length 4, and then it's suddenly like as you were talking about like error accumulation increasing or the model being just having the context of all the different tasks throughout it. Like this, I expect this kind of graph to change over time in the sense that this flattish line will keep moving towards the right, but the vertical jump is still dependent on your filtration process. So I don't expect that part to change. Yeah. Yeah, this is just the math for like the point I was trying to make is that RL is less of an exploitation kind of thing, but more of an SFT on optimized data. You're trying to optimize both the data that you SFT the policy on and optimizing the policy to generate data that is good for it to reach the goals. So it's quite static, not as dynamic as most people think.
I was just going to ask about this itself. So as you said, you try to use RL to filter out the good data and then use that for SFT.
That's what the reward model does, yes.
So correct me if I'm wrong, but what if you kept the bad trajectories as well with the lower reward? Won't that also update the
Yes, it does. Yeah, that's how you get, if your reward model is not that good in differentiating between bad trajectories and good trajectories, then those bad trajectories will be kept in the data, and each time it will increase more and more, and that's why V3 versus R10 have such a big difference in the amount of reward hacking that they do. Like that's the only difference between the two models.
Without SFT, that would still happen, right?
Yes, like there's a floor, like you have to have a floor, which is like in the initial set of data, the pre-training data that you train the model of. If the pre-training data contains certain reward hacking trajectories, then the model is going to have those trajectories in its weights. It's just that RL loops make it easier. It's not the RL part that makes it easier to pursue those trajectories, it's the loop where the reward model just keeps those trajectories over and over again in the data, and you like amplify that behavior. I'm gonna skip because of time. And when you harden the environment, like you're raising the complexity of the reward hacking solutions. So like if you just don't let the model access the test files, it can't really access the test files, and it doesn't even attempt to like even if it attempts, it doesn't like end up actually pursuing reward hacking trajectories. So like just your hardness matters a lot, in terms of which trajectories the model ends up pursuing at test time. And of course, if you're training the models, then those trajectories will be filtered out, and then in the next step, you won't have those trajectories and reduced reward hacking. Like it's pretty much like pretty effective, like hardening the environment is pretty effective in removing reward hacking even at test time.